turn the meeting. I'll turn the meeting over to Catherine to introduce tonight's speaker. Catherine?
Thank you. Tonight's speaker is Todd Thompson. He is the director of the Indiana Geological Survey and State Geologist of Indiana, and serves as the institution's chief executive, providing overall leadership and fulfilling the mission of directed science, service, and education. Todd has worked at the Indiana Geological and Water Survey for almost 40 years in several different capacities. Todd is internationally recognized for his success and long-term commitment to understanding the coastal geology of the Great Lakes, and has authored numerous articles, as well as passing on his extensive knowledge to students at Indiana University. Todd received his PhD in sedimentology from Indiana University, and I am very interested to hear his presentation tonight. So thank you for joining us and sharing your knowledge with us, Todd.
Thank you, Catherine. I really appreciate it. I'm going to go ahead and share my screen. How am I doing? Everybody got the screen right now?
Excellent. Yep.
All right. So, I didn't really know what level of audience that I was going to have here. So, maybe for some of you, I'm going to be not as technical, and maybe for others, I will be as technical. But as I was putting the presentation together, I decided that it wasn't as much fun as I wanted to. And one of the things I really like to talk about is the Indiana geology. And let me see if I can get my screen to move. There we go. One of them is Indiana limestone. So I'm gonna also pivot a little bit later on in my talk and talk about Indiana limestone, which is the premier building stone of our nation. So bear with me for a little while. So I'm going to talk about the bedrock geology, bedrock versus superficial geology in Indiana. I'm not going to spend a lot of time with superficial geology. We could spend a whole 3-hour talk on superficial geology of Indiana, but I'm going to focus on bedrock, rock distribution, features that we have in Indiana, and then I'll get into stratigraphy. And when I get into stratigraphy of Indiana, I'm going to focus almost entirely on Salem limestone and what it looks like and how we get it out of the ground. So it's really kind of a fabulous stone that I've spent quite a bit of time working with. So these are two maps of Indiana. One here on the left is the bedrock geology of Indiana, and the one on the right is the superficial geology of Indiana, or unconsolidated material. And so all of this stuff on the right is sitting on top of the stuff on the left. And so the only part of Indiana that is not covered with glacial debris and fluvial debris is this very southern area of Indiana down here, this sort of, if you want to call it a driftless area, down in the southern part. So I'm going to spend most of my time talking about the bedrock geology of Indiana. As many of you know, the people who study bedrock and the people who study unconsolidated, they have entirely different terminologies that they end up using on how they describe the material. I don't even think they like each other. And I study both of them, so I know that neither one of them likes me at all. So this map over here in the bedrock geology is showing the colors on here are related to the age of the rocks, where we have the Ordovician rocks in the southeastern corner, Pennsylvanian rocks here into the southwestern corner of Indiana. So the glacial material, mostly we're looking at 3 lobes that came into Indiana. One was the Erie lobe that came down in this direction. The other was the Saginaw lobe up here in the very northern part. And then there was the Lake Michigan lobe, which came down this way, and it got hit by the Lake Erie lobe and pushed it all over into Illinois. So most of you over in Illinois, you're looking at all things that come from the Michigan lobe. So we have more recently been working on the southern boundary here in Indiana. This would be more of not the Wisconsin limit, but the previous one, which would be the Illinois limit. We have a technique in Indiana where we do optical stimulated luminescence. So it's the last time that quartz grains have seen sunlight. And it looks like the ice was down here at about 160,000 years ago. And then it pulled back out of the Indiana, and then advanced forward during the Wisconsin to a boundary about right here around 24,000 years ago, bounced back past Indianapolis, and then re-advanced around 22,000 years ago, and then started this slow but sure retreat out of the Erie Basin, out of the Saginaw area, and then out of Lake Michigan, eventually here about 18,000 years ago. So that's it for unconsolidated material. Over here, you might notice that it's very rugged in the southern part of the state. And then it's very smooth in the northern part. And you'd say, oh boy, it's all really smooth up there because the glaciers all plowed it all off. Actually, the reason it's smooth up in this area is that all of this is we understand the topography of the bedrock surface based on holes that we've drilled into the ground, and we just don't have enough data up here. So it's showing it very smooth. The glacial material here in the very northeastern corner of Indiana is about 400 feet thick. So there's quite a bit of material there, and it thins down into the southern part where it goes from 0 to 25 feet thick. So I'm going to spend the rest of my time talking about the bedrock geology of Indiana. So Indiana is essentially a large anticline. It's known as the Cincinnati Arch or the Kankakee Arch. So this is the shape of this anticline with our oldest rocks here in the southeastern part of the state, and the southeastern, and the youngest rocks down here in the southwestern part of the state. So those that aren't really familiar with this, here's an anticline. I don't really know the level of my audience here, but here's an anticline, and when you truncate an anticline, you end up getting the oldest rocks are exposed in the middle with younger rocks on each side. If we look at it from a different view of a block diagram, here's an anticline here, and we're exposing the older rocks in the inside and the younger rocks to the outsides. But if we take this anticline and we actually plunge it, so we dip it in a certain direction, the anticline ends up making on the surface pattern a U-shaped pattern like this. So we're still seeing the anticline on this side, but we're seeing a U-shaped pattern on the ground surface. And then we're going to take that up to a bigger size and call it an arch instead of just a simple anticline. And with an arch, what you're going to have is rocks that will pinch out or thicken or thin over top of that arch. And so if you think of this pattern here, and you look at Indiana, here's the U-shaped pattern of Indiana, where we're having rocks that are dipping into the southwest and rocks that are dipping north into the Michigan Basin. And we also have rocks that dip in this direction over into the Appalachian Basin. So this large Cincinnati or Kankakee Arch, whatever you want to call it, is separating the Michigan Basin to the north, the Illinois Basin to the southwest, and the Appalachian Basin to the east. So here's Indiana again. This is the Cincinnati Arch here. We're showing that the rocks are dipping to 15 to 20 feet per mile to the north and 30 to 50 feet per mile to the southwest. Then they're dipping into the Michigan Basin to the north and to the Illinois Basin to the southwest. And those of you that might not be familiar with a basin, you just think of a whole series of nested mixing bowls, and one mixing bowl is smaller than the other, and a smaller and smaller and smaller one until you have no space left at all with that. I like to look at it with this. I found this a long time ago. This actually is sawdust that came off of a woodworker's table saw, and you can see the different types of wood that he has come into his bin. And I want you to think about this as basins, that simply the rocks themselves, some of which make it entirely across the basin, although some of them don't make it the whole way out of the whole thing. And so if you trunk it off here at the top, that's essentially about what the Illinois Basin would look like. And it depressed through time, and it continued to allow more and more sediment to accumulate into the basin itself. I think this is a really good example of showing what we need to figure out as geologists, because the only way we know any of this is by drilling holes in the ground. In Indiana, we have a number of different faults that are named fault. We have the Royal Center Fault in the northern part of the state, the Fortville Fault, and then there's the Mount Carmel Fault that's down here in southern Indiana. I really think there's a lot more to the Mount Carmel Fault, that it actually extends entirely around this area. What it is as a basin like this is subsiding, material along the side of it have to crack. And what's happening is the Mount Carmel Fault is a series of an echelon faults that extend around the margin of the Illinois Basin here. There's another series of faults that are down in the southwestern part of the state, which is the Wabash Valley Fault System. It's also over in Illinois. Most of these faults extend clear down into the New Madron Zone. not really seen much activity on any of them. The only one we know that's been moving during the Quaternary is this carbon fault that runs down here into Mount Vernon. There's been some research here that shows that there's some Quaternary sediment that appears to be offset from the carbon fault in this area. So there was a number of years ago, there was a geologist named Lloyd Furr that worked at the Indiana Geological and Water Survey, and he felt through a lot of the mapping that he was doing that there may be a lot more faulting in Indiana than we actually have name faults. And he suggested that there was a whole series of faults that extend from the southwest up to the northeast like this, and that there was also a series of ones that go from the northwest to the southeast. Did I say that right? Southwest to northeast and northwest to southeast like this. And he suggested that you might actually be able to see that in the bedrock topography. So here's a cartoon of the bedrock topography. Indiana has been above water for 300 million years, so it's along these faults where drainages and stuff would probably develop because the ground would be cracked in the area and more easily be able to erode. So if we put some things on here, you can see that here's some of the drainages that are following that northeast to southwest fault, and here's some drainages that are following that northwest to southeast drainage. And I really like looking at the Ohio River. If you get down to the Ohio River and start looking at that, you can see that the Ohio River has this reticular pattern like this that's pretty much follows that same fault pattern that Lloyd first suggested many years ago. I don't know whether this is true or not. It was a really good study of his. He looked at a lot of holes in the ground. There's no way we would ever be able to collect enough data to actually prove it. I mean, it would be nice to have a lot of seismic lines that would run across the southern part of the state, but we just, that's millions and millions of dollars to try to do that work. But I think Lloyd has a good idea here out of the whole thing, and I really think it's really fun to see how all these bedrock drainages follow that pattern that he used stratigraphy for to end up seeing a geomorphic and topographic pattern that goes along with that. In Indiana, we also have jointing systems. So you have faults where you're actually getting movement along the fault, and you also have cracks where the ground is just cracked. And in Indiana, we have cracks that primarily go at about 85 degrees. There's a prominent east-west jointing system like this. And then there's another jointing system that runs closer to north-south. And you can see that along many of our drainages. This is McCormick's Creek in that would be in Owen County in Indiana. And so this is the east-west jointing system, and then the north-south jointing system comes in the other direction, and it kind of breaks the rocks off in that pattern in the opposite direction. It makes a series of blocks with that. Joints are really very important in the bedrock because, bedrock doesn't transmit water very well, and the jointing systems happen to be a way in which most of the groundwater is actually going to flow through bedrock systems. And so in Indiana, this jointing system becomes extremely important on our bedrock groundwater flow. And even when you start looking at the distribution of sinkholes that occur at the surface, many of those sinkholes will occur along that east-west jointing system within the state. So many people think about the ground surface underneath their house and stuff like that as being flat. The rock surface is flat. You see the dirt and you think, oh, well, it's just going to follow the dirt topography. But many years ago, here near Bloomington, Indiana, there was a quarry, and name won't come to me right at the moment, but they were deciding to expand their quarry in this area over here. And so what they were doing is, heaven forbid, but they were taking actually pipes and they were washing the dirt off of the rock surface into the drainage system. So this was the early 1900s, and they 1904 something. We wouldn't do that today, but what I really wanted to show you is that this is that east-west jointing system. And you can see that the bedrock surface is not flat as a pancake. And you often watch when people are putting in a bedrock or putting a new building in, and they're doing all these probes and other drilling, and you're going, why? You're wasting all this money, doing that. It's just flat as a pancake. Well, it's not really. This is really what a bedrock surface looks like underneath the dirt in a carbonate terrain like that. So I just thought you'd get a chance for you to see what it looks like. And also, when you get into those kind of terrains like that, what will happen is that east-west jointing system will often expose itself into a series of erosional pipes or so down into we often call grikes. And these grikes are filled with clay. out of so when you think about this is where you're building your house, and this is what you're building your house on. These open voids and stuff that are underneath it like that. So, but that depends really on the rock that's underneath you. So here's a situation. This is all the Indiana limestone. So I'm going to talk about that a little bit later on. And there are joints here. We're looking west, and so we're seeing into the east-west jointing system. And where there's a little bit of St. Louis limestone still above the Indiana limestone, notice that there's no real exposure. There's no grikes or anything. But as soon as that St. Louis limestone is gone, all of a sudden the Salem limestone opens up into a whole series of grikes and other things. So it's kind of, depending on the geology or the unit that are underneath your house, you're either going to have these big open voids or you're not going to have these big open voids. When they were putting in State Road 37, I don't remember, that would have been in the 1960s, early 1970s, they actually found a full dire wolf skeleton in one of these grikes along the road like that. That's kind of a cool story. We have a meteor impact crater in Indiana. It's up here in Newton County, the very southern part of Newton County. It was circular at one time, but later faulting truncated along the southwestern side of it. And so in this case, this bolide came down and it smacked right into the earth straight down, and it caused the rocks to go down, and then they bounced up, and they're sitting almost vertically straight up like this right now, which is really pretty cool. I think, and they're all shattered and broken up like that. So we're looking down on a series of rocks that are looking straight up at us right here. And since all the rocks around there are the Mississippian Borden group, which is mostly fine-grained sandstones and shales, there's no nearby limestone. And so everybody needs aggregate. And so this actually exposed older Ordovician aggregate in the central part of this area. And so the Rogers group went ahead and put a quarry in there. And so there's a quarry inside of this former meteor impact crater where they're actually able to get aggregate, because most of you know that you don't transport limestone more than about 30 miles. It transport more than 30 miles and it's no longer economical. So in this case, in an area up in here where we don't have any exposed limestone, they now have a source of limestone for the citizens that are part of that area. So if I could drill a hole in Indiana in one specific place, and I would start from the ground surface or the bedrock surface, and I would start drilling down and down and down. So I'm adding this one on top of this one, and this one on top of this one, and this one on top of this one. What we'd end up having when we first started is we'd have mostly sandstones, which are the yellow. We'd mostly have blue, which is the limestones, and the gray, which are shales. And if we kept drilling down, we'd start hitting some coals. And we'd have coals and we'd have shales and sandstones, not so many limestones left around anymore. And then we'd have some more coal and more coal. And then we come down to this little squiggly line, which is an unconformity surface. And so there's a major unconformity between the Pennsylvanian and Mississippian rocks, where this unconformity can barely cut into the Mississippian rocks to the point that it'll actually cut clear down into as far down as here into the Borden rocks as you move up into the northwest. So ignoring that unconformity, after we come through most of this stuff that was coals and shales and limestones, we end up having limestones and sandstones and limestones and sandstones and more limestones and sandstones and more limestone and sandstones. And what was happening here is we were building the Appalachian Mountains. And so as we were building the Appalachian Mountains, as Africa was smashing into North America, we would shed siliciclastic sediment off into the Midwest. And as the mountains would erode down and shoot less and less sediment off into the Midwest, we'd get these carbonates that would form in between each of those sandstone units. As we get farther down, we've flooded the continent. We have the Blue River group, the Sanders group, which are mostly carbonate units, primarily limestone. We have a large delta that came off of the Appalachian Mountains, which is the Borden group. It's very thick, as much as 700 feet thick. And below that is a black shale. And that black shale is the New Albany shale. And for the Illinois Basin and most of Indiana, that dark black shale is the source of almost all of our petroleum as well as natural gas for almost all of our rocks. So it came up out of this organic material, came out of here, moved up through fractures, joints, as well as through the faults, and populated these areas to the north, to the above it. And then, so there's the New Albany Shale. And then once we get deeper and we get deeper and farther down, we have mostly these carbonates, almost all dolostones, as well as limestones. And of course, as many of you know, everything starts out as a limestone, and a dolostone is diagenetically changed from that. But we have about 200 million years of accumulating mostly carbonates along the eastern edge of the Illinois Basin. As we go farther down, we get down into the Maquoketa group, where we have mostly carbonates, but we have quite a bit of shale again. We haven't had that for a while. And most of that shale is part of what's known as the Maquoketa group. When we go farther down into it, we end up getting some more carbonates, as well as sandstones, more carbonates, and then we get a thick sandstone down at the bottom before we get on to very deep crystalline rocks at the very basement area. So any of you that might be interested in carbon sequestration, you want to get below 2,500 feet, and we have 3 units below 2,500 feet. So Indiana is a target for a lot of carbon sequestration. This is the St. Peter Sandstone. The Potosi Dolostone down here, as well as the Mount Simon Formation, are looked as targets in which we can sequester carbon. And the Maquoketa group is used as a seal that would keep that CO2 from ever making it back up to the surface like that. So that's kind of the main units. These are the exact same units that you would end up seeing in Illinois. However, once you move into the Illinois Basin, all the thicknesses thicken up to double from what you'd end up seeing along the eastern margin that we have in Indiana. So that's mostly, you know, the differences between the two of us. I don't want you to think about each of these units as being flat pancakes. This is some of our Silurian units. You can see that this is now I got to put my glasses on. This is about 600 feet thick here. This is where the Silurian rocks are missing in the subsurface, but then they thicken down here in the Illinois Basin. And so it's fairly common for that. Here's the Black River Groot, about 100 feet thick. But by the time you get down into the toe of Indiana, getting into the Illinois Basin, it's about 500 feet thick. The Ansel group does pretty much the same thing, but look at the Maquoketa. Maquoketa is kind of entirely the opposite. It's very thin up here in the northwestern part of the state, and it's thinning down to the southeast until it's missing over the arch. And then my favorite one over here is the Trenton, where it thickens to the northwest, and it thickens down into Kentucky. But then there's this group, this area down here in the southern part of the state where there's no rocks at all. So how do we know this? How do we know what these patterns look like? I'm sure you're all aware we plug holes in the ground. So we have about 90,000 some wells that have been drilled into Indiana. Most of the oil wells first came up in here in what's known as the Trenton Field. We have the area up in here where we have a clay city and gas city and oil city up in this area. This was one of the largest early oil and gas fields in North America. And so the gas was only down about 650 feet below the ground. At one time, we had 15 glass factories in these counties up in this area where the gas was very plentiful. They had street lights where it was burning gas because, as you guys all know, this gas was going to go on forever, and forever was about 25 years. And so, that's about how long it is. So whenever you're thinking about forever, it's about 25 years. So all the exploration for oil and gas moved away from the Trenton Field. There's still people that are doing that, and most of the production is now down in this southwestern part of the state. I did want to point this out here. This is some of the drilling that's occurred along the Mount Carmel Fault, because there's an anticline along the western side of the Mount Carmel Fault. And what happens, in early 1900s, they pulled gas out of there. And now today we bring gas up from Texas during the summer months, and we pump it back into the ground. And it's easier to store gas in the ground than it is in a tank. And then we pull it back out during the winter months when it's nice and cold. So a lot of the people that live here in Monroe and Lawrence County have liens on their property having to deal with oil and gas rights underneath it. And they're always calling us at the Geological Survey, asking us questions about, why is there a lien on my property underneath the ground? And nobody's doing any production there anymore. It's just that we are still pushing it into the ground and pulling it back up again. This is where that meteor impact crater was, up in Newton County right here. There was been quite a bit of drilling around that meteor impact crater itself. So I'm going to pivot for just a little bit and talk about something different. In Indiana, when we talk about the stratigraphy, it's very similar to Illinois, but we have one thing that Illinois doesn't have. And we have this unit that's called the Salem limestone that occurs right here. So this is our Mississippian rocks. And there's a unit right here at the very top of this is called the Sanders group. And it's exposed in an outcrop belt that runs down through Monroe County, down into Bedford, and it goes on down into Washington County in this direction. And we can take it as far north as Putnam County. And so it's in this very narrow belt here, no more than 30 miles at the most wide, where we're pulling out what's known as the famous Indiana limestone. And Indiana limestone graces a lot of buildings across the country, and most of us as geologists see it like this, as my colleague Brian Keith was doing a video. You can see how thick the limestone is with no real breaks or anything in it. And those of us who get into the quarries see it looking like this. But most of you end up seeing the Indiana limestone looking like this. This is the National Cathedral. This is the Holocaust Memorial, the Pentagon, as well as the Empire State Building. And if you're ever watching NBC News in the morning and they go to the Rockefeller Center and they spin around, every one of those buildings you look at is made out of Indiana limestone. So why is that? What's really important about Indiana limestone that makes it so good? Well, first of all, it's hard enough that it makes a good building stone, but it's soft enough that you can actually carve it and manipulate it quite a bit. So let's think about Indiana limestone. What was it like? Here we are about 340 million years ago. I'd probably take us closer to 350. In that time, North America was sitting here. This is the Appalachian Mountains. Here we're turned a little bit. We're 10 to 15 degrees south of the equator. And at that time, we're sitting in the carbonate factory. Let's face it, this is where any organism that really wants to use calcium carbonate to build an external skeleton or an internal skeleton love to live here. And when they die, their body parts are going to accumulate in that area. So it's just great time to be in the carbonate factory, and that's where we were. And so I decided to go over to the physics department about 3 months ago, and I asked them to give me a time machine. And so I went back in time. The physics department can do that, and this is what it would have looked like. Here in Indiana, 345 to 350 million years ago. It was a large carbonate shoal. This is a white sand that you can see here. This sand is not quartz sand. The sand is all carbonate sand. So if you took a big fire truck and of hydrochloric acid, you could fizz it all away. And so what you would end up seeing is that there are these large sand waves, and these sand waves are moving on shore onto the shoal body itself. There happens to be these channels, these intrashoal channels that cut between it. And if you follow one of these intrashoal channels, they go into spillover lobes on the landward side. So you follow one of the channels, and you're seeing this sand being shot back into a lagoon on the landward side of the shoal. And this is what it would look like. Here's some older spillover lobes and some younger ones that are in here too. Now today, this is actually pictures from the Bahamas, and today in this lagoon there's primarily grasses that are growing in this underwater area. But during the Mississippian, it was mostly fenestrate bryozoans. So there was an animal there instead of a plant at that time. Here's a cartoon, to try to show you what I was really talking about. And so this is a buildup of carbonate material here, which you call as a shoal. And so it's out here in this upper shore place where organisms, bryozoans, crinoids, and other things are living. And when they die, both tides as well as waves would drive that sediment on shore and build it up into the shoal body itself. And so there's they would build up this thing, and then it would go into this lagoon on the landward side, where the spillover lobes would go into that lagoon of primarily a bryozoan rich carbonate at that time, and then finally move even farther landward, where you'd have a restricted lagoon and an intertidal flat with stromatolites and other things that you might expect during that time period. And so water would come over top of the shoal, go in and out through the through the intra-shoal channels, but then the rest of the water would get stuck in the lagoon. It couldn't get back over the shoal, so it moved laterally along, and it would come out through these intra-shoal channels. What's really interesting about this is that if I put State Road 37 in Indiana, it would pretty much run right down this shoal. And so in the Bloomington area, we have a thick shoal complex. And then as we get to the south of Bloomington, we have this inner shoal body where there's these little thin shoals. And everybody who's tried to open up a quarry, they don't have very much stone, don't go very long. It's very, very, discontinuous and not a good quality stone. But then you get farther down south, get closer to Bedford, and then you get thick shoal bodies again. And so it almost this, the whole outcrop belt kind of follows this pattern that I have right here. I really like going to the inner shoal area because there's some tidal channels where we find tidalites inside of these channels that show many years of sediment accumulation. So just to remind you, here's one of these areas. If we take this part of the shoal, here's the sand waves that are moving up into the main part of the shoal with the inner shoal channel in between it. So I'm going to step aside here just a second and talk about these sand waves that are moving up through here. So these are essentially ripples. You can think of them as nothing more than a ripple that can be anywhere from a centimeter or two thick to 2 to 4 meters thick. They all behave pretty much the exact same way. These are straight crested ripples, but once you get into the inner shoal channel where you're funneling higher velocity sediments, the ripples themselves then start getting a three-dimensional look to them. So here's a ripple. And so here's a couple ripples. And so as many as you know, grains come along and they bounce up the back of the ripple. It could be a bigger sand wave if you want, and they avalanche down the front. Some of them continue over and avalanche down the next front of the next ripple over. So the end result of this is they end up producing cross bedding within the ripple, and it looks like this. So this is a picture from one of the quarries, and you can see this is a 6 feet long stick that's being hung here. And so you can see this is a fairly thick bed form of very light and dark foresets that are here in the bed form above. They're coming down tangential to the basal contact like that. And so if you haven't ever spent any time with ripples, here's what ripples do. They migrate along like this. And one ripple migrates through the one in front of it. So if there's no increase in sediment supply, ripples do nothing. They just move along happily as they could be, like they were going through a culvert. Nothing gets accumulated at all when a ripple moves forward. But if there's a positive set of sediment supply, what happens is that one ripple will climb up the back of the ripple in front of it. And this can happen from very small ripples up to big sand waves. And so this is how you end up getting cross bedding in a rock unit like that. These are planar cross beds. So what it's showing is that there's actually, I'm using my hand instead of my pointer, sorry. We end up having a straight crested bed form like this. It's migrating this direction. What we're going to do is actually turn this bed form in just a second. So if we watch it just a little bit more, we're going to say, what happens if you cut this bed form in a lot of different directions? If you cut it where you're at an oblique angle to the crest of the ripple on both sides, you're going to see cross bedding on both sides. If you come clear around to the other side, it'll look like the first side, when the left side, and we're going to be in the right side. But here's what I want you to see eventually. If we cut this block vertically, and we'll let it go for a little while, you'll see that this cross bedding that occurs on this side ends up being spread out as a series of foresets and stuff when we see them on the top. And the quarrying industry a long time ago recognized that, because the architects don't want to see this, and the architects don't want to see this. They want it to be more innocuous. They actually want the stone to look more like concrete, which is sad, but that's what they wanted to look for. So they learned a long time ago that if they cut the blocks, parallel to the surface and hung that up onto the building, that they wouldn't show the cross bedding as much as it would before. So here's another situation where we have a three-dimensional ripple. So in this case, it's a higher velocity scenario, and we're moving that ripple along. And what ends up happening is on the one face, we get the typical cross bedding, but notice that on the other face, instead of the horizontal laminae, we get these trough cross beds with this. So this is trough cross bedding. And I'm going to let this one run for a little while too, because it's kind of fun to watch the patterns that go along with it. So when you're cutting a block out of the ground, you don't, especially the quarry industry, they don't know this. They don't know anything about paleocurrents. So they don't know what's the best direction. So they're always cutting the blocks out just based on the property lines that they end up having. Actually, they mostly cut north, south, east, west because their dad did it and their grandfather did it and their grandfather's grandfather did it with that. But as we turn it around in the other direction, you'll see that now we're looking in on the crossbed instead of looking at behind it. We're seeing the trough crossbedding here and we're seeing it. But here's what's really cool at the surface is how much different the trough crossbedding looks on the surface from the planar crossbedding. We'll let this run. So that's kind of a pattern. So what we have in the quarry industry is sort of two bed form types that we end up seeing. One is the planar cross bedding, where we have the straight crested sand wave, and that's going to make cross bedding along the one side, pretty much horizontal on the other, but very spread out foresets on the bedding plane surface. And then we have the trough cross bedding, where there's quite a bit of more variability on the one side, and we see the troughs on the other side. And if you go to a building and look at it, this is planar crossbedding. So this is up here where they've cut the block parallel to the top, and then they've hung it up on a building like this. And here's your planar crossbedding. And here's one where we have the trough crossbedding, where you can see the troughs that are on the top of the bed like that. So there's a lot of different types of bed forms that occur, but this would be a higher velocity bed form. Mostly they're hanging planar cross-bedded kind of stuff on most of the buildings. Here's the cross bedding. I want you to point out, notice how this surface between the one cross bed and the other is not flat, because this bed form climbed over top of this one along the way. So it has to climb. You have to have a positive supply of sediment to actually preserve a bed form. Without it, this bed form will just migrate through this one happily as could be. There's also hard grounds in this. And so this is what's kind of interesting about when you go down to the Bahamas, or probably also occurred during the Salem time, is that if you have carbonate sediment, that carbonate sediment can start to lithify into rock in 2 weeks or less. And what's happening is every time that water goes across the surface, it's certainly moving water that's rich with supersaturated with respect to carbonate, but it's also pulling water through the grains that's supersaturated with respect to carbonate. And what ends up happening is it ends up cementing the rock within 2 weeks or less. And so in this situation, here's one of the quarry walls where this is a cemented surface with an overhang, some clasts and other kind of stuff there. And when the next bed forms came in, they climbed over that very irregular cemented surface that probably got ripped up during a storm or something like that along the way. So you get to see these hard grounds that occur in the quarry walls. But again, notice the climb. This bed form had to climb over this one, and this bed form had to climb over the other one. So they're always climbing bed forms that you end up seeing in the quarry. Here's another example. One of the things we were looking at was what's the difference between the light and dark laminae that you end up having, and I can explain that in just a minute or two, but it's kind of hard to see. But there's another hard ground surface that runs right through here with an overhang that hung onto it. And so these bed forms, look at them climbing again in this case, they're climbing to the northeast or onshore. This is a very big overhang over here, and it's hard for me to draw it because your faces are all in the way of it. And so there's a big overhang over here, and attached onto the end of it is sort of a stromatolite thing, which is called a thrombelite. So it's a stromatolite that is not really well formed with good laminae on it. It's kind of thrombosis or a clotting kind of thing on the very end of it here along the way. We also get stylolites in the quarry itself. You don't typically see these on the building because they're not structurally very sound. But generally, you'll end up having these sawtooth kind of looking stylolites that'll show up in the quarry walls. They often carve those out, so you never see them on a building. But some of the teeth are really pretty amazing. And often on the tops of the teeth, you'll end up getting organics as well as iron that will accumulate on the teeth, because what's happening is the rock are dissolving into each other on each side. So any leftover organics or as well as iron won't dissolve away. So it gets accumulated on the crest of each one of these fingers of the stylolites. So what did we have here? I mean, mostly we had crinoids. I mean, that's the dominant material that makes up the Indiana limestone. You're all familiar with this. They're really an animal instead of a sea lily like everybody talked about. I mean, I love this one where one of them decided he didn't like the neighborhood and decided to move somewhere else. So he gave up his holdfast and started dragging himself across the ground. I mean, this has really helps you out to understand that these are really animals and not a plant of some type. I just love this picture. How come I never find anything like this? It's just amazing looking at the calyx of a crinoid and all the feathery material that's in between each one of them to help it filter feed. Blastoids were really pretty common too. You know, entirely different head on them. You know, the theca on the blastoid is very different than the calyx. We often find them in the rock looking like this. You know, you'll see the pentagonal look to them, but they look like little acorns a lot of times. So you'll find it often along a hard ground surface where these acorn-like heads of the thecas will end up showing on the Indiana limestone. You know, fenestrate bryozoans. I mean, Indiana limestone is often called you know, it's said to be oolitic as well as being very crinoidal. My experience is most of it, it's actually ground up fenestrate bryozoan material. And what'll happen a lot of times is if you break off, you know, this little piece of this fenestrate bryozoan and you grind it up, it ends up looking like an ooid. And so I think a lot of what it was called oolitic limestone is not oolitic limestone. You know, if you pull up anything about the Empire State Building, they'll talk about being oolitic limestone. You know, come on, the bottom line of it is ooids in the Indiana limestone is maybe 3 to 4%. You know, it's hardly any. We have oolitic Indiana, and there aren't any ooids at oolitic Indiana. So there's your trivia for Indiana right now. These are the hold, you know, the holdfast are down here, and a lot of times on some of the surfaces you'll end up seeing these holdfasts will end up showing along that in the quarry walls. The Indiana, you know, the Endothyrobalei is considered the diagnostic fossil that you end up finding in Indiana limestone. You know, it kind of looks like a little pumpkin. It's not as common as everybody says it should be. You know, it's really kind of hard to find. It'll occur more in the lagoonal facies and the sandflat facies than it will in the major part of the shoal with that. We also have stromatolites. So many of you are familiar with stromatolites. They occur in the Bahamas today. We find stromatolites in the Salem limestone. So you can see these snow cone-like stromatolites that occur here. Some of them became kind of big. This is one of our graduate students. You can see this one's almost as big as her. And in one of the quarries, we actually spent some time as they were taking all the quarry walls down. We would map the stromatolites out along the surface of the quarry walls. So the yellows are stromatolites, and the greens are colonial corals or Serengopera corals that would occur in the face. You can imagine that the operators of this quarry didn't like these very much. Most of this stone ended up getting thrown away. And eventually, you know, after them working in this one quarry, it's a crown quarry south of town, for about 10 or 12 years, they abandoned the entire quarry. And so because they just couldn't get good stone out of it. You will find occasional stromatolites on certain buildings, but generally the quarry industry, if you bought a block from one of the companies, you know, you'd send it back to them saying, hey, it's got these stromatolites in there and I don't really like to see them. You know, every so often we find some really unique things. You know, here's an ammonite that occurs in it. I tried to get the guy to give us the block, but he wouldn't give it to me. But anyways, they cut it open, and I think it's just kind of a spectacular view of the chambers that occur through an ammonite, something similar to this. Wish he'd give it to me, but he wouldn't. So we find sponge spicules on hard ground surface. We have these Bellerophon gastropods. So this was a hard ground surface that got broken off, and you're looking at the bottom of that surface right now with it. So these are the size of golf balls and sometimes a little larger than that. You can imagine that if you're a gastropod and you're trying to move around through soft sediment, that's kind of hard. to do. But if you have a hard ground surface, you can move around it very well. And so we find these bellerophonic gastropods fairly common on the hard ground surfaces, almost exclusively on the hard ground surfaces. There are also trace fossils. This is a view of a quarry wall, and you can see there's a trace that came up through here, and he got buried by the next bed form that came over, and the next four sets that came over, and the next four sets, and then he maybe moved over here and he got buried again, or he moved over here and got buried again, and then he just decided to go to Vincennes and just get the heck out of the area with that. There's also these worm traces down here, so you can see that you'll see this a lot. So now that I pointed out to you, if you're looking at any of the buildings in downtown Chicago or those other places, you'll find these worm traces. It's known as Margaret Ignis. Is the trace fossil name. I know that because that was my mother-in-law's name. That's the only way I remember fossil names like that. But it's fairly common that you end up having this bright tube in the middle, and it glued together the side walls, and so you end up getting a darker pattern along the side walls. And then occasionally you'll see along the edge of it there'll be a little ball and another little ball and another little ball, and those were all the poop balls that came out of the back end of the annelid that was making it. So they're a really fun structure, and once they're pointed out to you, you see them from that point on. But prior to that, you don't really notice them very much. Here's the bottom of a slab in a quarry, and you can see a lot of even though the sediment was so poor with organic material, there was quite a lot of animals that were burrowing around through this bright white carbonate and pulling out any organic that they could end up eating. So I'm always amazed at the amount of tracks and trails that occur in Indiana limestone. These are real true ooids over here. Typically in Indiana limestone, you end up getting these rounded crinoid grains or rounded bryozoan grains, and then they'll have a little bit of a coating around the outside of them. So they're not true ooids. And the reason the term oolitic limestone, the Indiana limestone, became oolitic was in the late 1800s. A lot of the carvers and stuff were brought over from England, and they were working on many of the palaces and stuff where they are actually looking at a true oolitic limestone. And when they came over to Indiana and they ended up seeing these rounded crinoid grains, they thought they were still looking at ooids. And so that term oolitic limestone got brought into Indiana, and it's been stuck there ever since. Even a couple years ago, there was a publication from a prominent researcher in Australia, and he was talking about oolitic limestones in Indiana and the Empire State Building built out of oolitic limestones. And we had to tell him that his paper was really wrong. But he didn't like to hear that, but that's really, that's just really the truth of the whole thing. Okay, so if you want to get some of the limestone out of the ground, obviously you have to deal with the belt where it comes down here pretty much along 37. So, I wanted to make a cross section along here, but I couldn't dig a deep enough hole. So I drilled a bunch of holes along through there. And so here's some cores that we ended up collecting. This is the Salem limestone right here. And so here in this area from here to here, you could put a quarry in. But once you get over to here, you can see the Salem limestone is too far below the ground, and you can't put a quarry in there. However, we do have underground quarry, and I'll show you some pictures of that in a little bit. If we followed this Salem limestone, because it's dipping at 30 to 35 feet per mile to the southwest, we go another 30 miles down toward Bluefield. It's over 600 feet below the ground, and now it's a reservoir, and they're using it. They're pulling petroleum out of the ground from that exact same rock. So it's used in a number of different ways. The earliest technology to get it out of the ground was mostly horsepower and hand drilled ledges. By in the late 1800s, they introduced these coal-fired steam channeling machines. Oh man, I can't imagine working in there with all that smoke and stuff that was. You could see all the soot and stuff that was on top of the stone at that time. And then they moved over to electric powered machines later on. These are channeling machines, so they're not really sawing. They're just essentially a series of chisels going on the rock and just going back and forth until they chiseled down to whatever depth they needed. By the mid 1900s, they used wireline saws. So there'd be a wire that would come over to a pulley and lay over the rock, and they would put Ottawa silica sand, along the wire, and that would help to cut the stone out of the ground. Later, and this is what everybody's using nowadays, starting in the mid 1980s, everybody started using these belt saws. And so it's sort of a big chainsaw, and it has a rubberized belt where you have tungsten carbide bits that are on both sides of the blade. And the blade is anywhere from 10 to as much as 15 feet long. They plunge it down into the ground. They also use it in the mills too. There's a saw blade right here. They plunge it into the ground, and they can back up 10 feet to 15 feet at about 3 inches per minute. So they can very rapidly cut a trench like that. So it's really kind of fun to see. Here's another example of one of the larger blades with it. And then once they knock the blocks over, they end up using front end loaders now instead of the derricks that you might expect would be used before. So they essentially, put row after row, and they have machine after machine after machine cutting. And then when they get to the end, they just turn it around, flip it over, and turn it around in the other direction and cut back the other direction. And that gives them a block that's roughly 4 feet wide by 10 feet long. And so then they have to break it up. So in the old days, they use slips and wedges, and now today they use these new hydraulic splitters that help break the rock up. So after they've turned to face over like this, they'll use the hydraulic splitters to make it much easier to break it up in these 4 feet by whatever, 4 feet by 4 feet by 6 blocks that they can get on a front end loader and move it. There's now an underground quarry. We have one underground quarry near Eureka, Indiana. This is how you get into it. And when you're down underneath there, it looks like this. It's kind of the same saw, but it's turned sideways. And so they end up making these sideways cuts, and then they make a vertical cut between the blocks along the way. And then they come in, and what's really interesting is they'll come up to the top and put an airbag in here, and it'll bust the first one, and it'll go, and all of them will bust off like that down to the bottom. And then they come in with a front end loader and pick out every block and carry it back out of the place. Here's an example from the other side. These machines are totally automated. They turn it on at night, and they go away. And when it gets done cutting in the morning, it turns itself off and reports home and says, "Hey, I'm done with what I need to do." And then they come in and bring in a front end loader and stuff to move the blocks away. The mills are practically no different than they used to be. Here's an older picture of using a planer. A lot of the same stuff that you do in Indiana limestone is like a woodworker does. You have got planers, you got Maynard saws, you got drills, and other things like that you might use. You got a chisel that's a little bit different, but everything's still pretty much the kind of the same technique that they've always used. They can turn things on a lathe, and it doesn't matter how big they are, and they have a lot of fluting machines that they can add the flutes. No, typically, they don't make a long column of flute like this anymore. They'll make smaller ones, and sometimes they're even hollow like that. And then now they have computerized saws that'll just come in and cut the blocks. It is program it now today. Some person stands there and watches them cut the block. And then, of course, there's always the skilled people that are going to come in with the now pneumatic chisels and chisel out flutes if they need to, or work with those Corinthian columns. So it's not a lot different. One thing you notice that none of these people are wearing any masks. In all the pictures I've shown you, nobody's wearing any masks. Well, the EPA has been here quite a while to look at this. The Indiana limestone is 95 to 98% pure calcium carbonate. So if you breathe it in, you're just breathing a Tums tablet into your lungs, and it just essentially dissolves into your lungs. So there's no silica in this that's going to cause any problems. And obviously, if you look at some of these mills, the people, when they come home every day, they're just covered with limestone dust, but they just seem to be healthy as can be. Okay, I'm kind of done now. I've gone, it says 9:57. I think you guys have had enough. I've had enough of a day too, but so I'm going to give you a little cocktail party trivia, because geologists are great at cocktail parties because we're loaded with a lot of trivia. So here's what happens. You're at a cocktail party and nobody's talking, and so what I'll do is I'll saddle up beside somebody and I'll read the first one, and I'll go, "Hey, did you know that Indiana is a big arch, like a big anticline separating the Illinois and Michigan Appalachian basins?" And the person will go, "Oh?" And I'll go, "Yeah, it really is." And then I use the next one and I say, "Hey, there's numerous faults that occur in the state, mostly occurring in the Southwest, associated with the Wabash Faulting System." And then another person moves over next to me and they go, "Well, that's really cool." And all of a sudden the hostess has got smiles on her face, and the party is just going, going great things. And so then I try the next one. I say there's pervasive joining that controls groundwater flow. Okay, that one doesn't work very well, and so people move away from me. So I go to other ones and I'll try out the stratigraphy of Indiana, is similar to Illinois, although the units are thicker in Illinois going into the Illinois basin. Indiana is famous for the Indiana limestone. I mean, 34 of the state capitol buildings are built out in Indiana limestone. All of the Federal Triangle in Washington, D.C., like I said, the Rockefeller Center, most of downtown Chicago is Indiana limestone. And some of the equipment has changed, the processes are pretty much the same. And seriously, people will use a regular hand saw that you would cut wood with to cut Indiana limestone. So it's that soft, but yet it's still durable with that. So I'm kind of done, and thank you. And if there's any questions, I'll answer as long as you have questions. So thank you very
I
much.
want to know how much is alcohol is pouring in at these parties at this point.
Well, when I start talking, usually pretty much, because anyways, that's kind of it. So
I have a question to I have a question, Todd.
yeah.
Okay, my name is Dave Dolak. I did my graduate work at IU and at the Dunes. Is Bob Shedlock? Do you remember Bob Shedlock?
I remember Bob Shedlock. He's retired from the USGS now.
Yes, so a lot of the water stuff I did at the national park in the 1980s and stuff. Anyway, and I work with Erin Argelin. I know you know Erin.
I do know Erin. She's one of my favorites.
So colleague up here. Anyway, question, just in your showing the stratigraphy, I teach at Columbia College, Chicago, but how come the Richmond group, did you sort of end with the Maquoketa group, and then just sort of left that blank there at the far Richmond or the Cincinnatian group? Is there any reason? I just was wondering.
So that group would go, it would go over this, that was that blank area in there.
Yeah. I mean, it's on top of Maquoketa.
It wasn't accumulating over the Cincinnati Arch. So at times the arch was elevated, and at other times we were having sediment just going exactly over the arch.
Okay, I guess misunderstood. That's why you're just showing.
Well, I didn't explain it, so it was.
It's a unit there. It's still there and named that. That's why I was confused.
Yeah.
Okay. Thank you.
I want to say that I could have slowed you down and listened for hours because there was so much information and I was learning so much. I thought the ripple sand movement was phenomenal. It was real easy to understand, but yeah, I think you need to come back and teach one of your full classes so we have more time to really understand everything, because it was a lot of information. Fascinating.
Thank you. So, those kind of pictures and stuff that I show you, there's a lot of people that work in the quarry industries, and they don't understand anything about the geology of the stone that they're pulling out of the ground. And so many of the images and stuff I showed you, especially those animations of ripples, they've looked at cross-bedding in their quarries for ages, and they don't understand it. And then all of a sudden I show how cross-bedding is made, and they're like, oh, this light bulb goes on. I did a presentation for the Indiana Limestone Institute about 10 years ago, and there was a lady there that's owned a company for 60 years, and she came up and said she learned more in the last hour than she knew about the stone in her last 60 years. And it's just really, these are not difficult geologic concepts. It's just that, the industry is, fossilized. So to speak. They have a way that they've pulled stone out of the ground, and they continue to do it the same way. The jointing system that I talked about at 85 degrees, they cut their walls at 90 degrees. So they end up having this 5-degree sliver that they leave, and it's along those joints where the stone gets oxidized, and so it becomes a buff stone, and they get 3 times more money for buff stone than they do for the gray stone. But yet they end up, because they cut the wall at 90 degrees, they end up with this 5-degree sliver that they throw over the hill because it's not big enough. And if they would just move their wall by 5 degrees to line up with that joint, they would not only have a natural cut, so they wouldn't have to cut it, and they gain more stone, but it's also those little 5-degree wedges that fall off and kill people in the quarries. So I've been pushing this one for 25 or 30 years. Bash, it's just like bashing your head against the wall because their grandfather did not do it, and so they're not going to do it either.
It was fascinating. I mean, utterly fascinating. I could have I want to know more about it. But yeah, and the crinoid movement, I mean, yeah.
Doesn't that look like something out of the movie Aliens, or something like that when they're crawling along in the bottom? What's also interesting about crinoids is, they occur primarily in deep water nowadays. We don't have them in the shallow water like we have to. And they're brightly colored, pinks and oranges and yellows. And they're in dark, so they're in dark water right now. So those things don't matter. And I think they're just left over from when they used to be in shallow water.
So, yeah, and some of the fossils you were showing were just, I'm going to now be looking closer at the walls, when I'm seeing some of these buildings, because it makes sense. Now that you've explained it, now you're going to see it. You're not going to not be able to see that.
Last Friday, I was doing a master naturalist class here in Indiana, and we got done with the first part of it, which was dealing with sedimentary rocks. And I said, let's take a field trip. And we just went outside the building with our hand lenses and stood around looking at the side of the building. It's just fun. Get a hand lens and get up close and personal with some Indiana limestone, and you'll get to see a lot of bryozoans and crinoids and blastoids.
Do you ever have any trips into any of the quarries for collecting?
No, I don't do any of that. I mean, you have to keep in mind my title is state geologist. That's not something that I'm going to be able to do. We don't typically collect in quarries, but I do lead field trips for quarries. Is Joe Kubel here tonight? I'm leading a field trip for him on the 26th of this month for the Illinois Geographic Society. We're gonna hit one of our quarries not too far from where I live here. Then we're doing a tour of the campus. So the campus has, these gorgeous buildings. I mean, those of us who live on Indiana University campus are so spoiled because we think all buildings should be bright white.
Well, I don't want to dominate on the questions, but so I'm going to let everybody else ask other questions, but fascinating information.
I have a question about the exposed bedrock. Isn't there some exposed bedrock on the far southeast part of the state as well?
Yeah, there's a little bit over there, and there's some exposed bedrock along the Wabash Valley fault system. There's exposed bedrock all along the Ohio River and the Wabash and stuff. So that I was
Because I've done some fossil collecting along near St. Leon.
Yeah, there's some thin glacial material that covers over that area, but it's it's in
Well,
0 to 10 feet.
Bedrock's exposed in the road cuts along in there. Yeah.
Come on, I'm still awake.
I'm curious, what are your job duties as state geologist? What are your
Yeah, I spent 30 plus years being an active geologist, doing quite a bit of work around the Upper Great Lakes, doing a lot of geological mapping in Indiana, and now I push bits around computer screens. That's what you do as a director. I edit a lot of things. I'm always looking at proposals and budgets and stuff like that. So it's a different career. But I do have a lot of younger geologists, and so I spend time with them describing core and other kind of things to bring them up to speed.
Sure.
Yeah, but generally I'm pushing paper, or now it's bits around computer screens. So
sure.
Yeah, it's not that much fun. I gotta tell you the truth. It's not that much fun.
What about the rocks around Terre Haute and sort of the coal mines in the western edge of the state?
I didn't spend much time talking about that because I focused on Indiana limestone, but obviously that's all our Pennsylvania age rocks that are loaded with the coal, and so there's a lot of coal mining and stuff that occurs in that area. One of the big issues right now happens to be subsidence over coal mines that were put in the early 1900s up to the 1940s. Many of those coal mines were just barely over 100 feet below the ground. And in those days, you didn't do strip mining. You went underground with that, and so we're starting to get subsidence. In the town of Chandler, we just had some subsidence a few weeks ago that damaged multiple homes.
Well, I'm just
subsidence.
gonna say the underground, nope, 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 not underground. Mm. Yeah, when I saw those pictures of the underground quarries,
Well, I did a field trip in there and we actually took a bus. So we took a bus in there and drove a bus into an underground quarry. It was really kind of fun.
Do they ever have to worry about subsidence in those too someday, or is that
They have had some roof falls, and so the typically the roof falls are actually occurring along that jointing system again at 85 degrees. And seriously, this was Rich, I think you asked that question. They
Correct.
make the walls north, south, east, west, and for the longest time at our organization, we've been arguing that they should actually place their pillars such that it goes from joint to joint to joint, so that you're getting support on that. So they have to come in and put roof bolts in with that. So they take the first 20 some feet out using that saw that I ended up showing you. And then they take the next 20 feet out, a couple benches down after that, using that same conventional way that I showed you above ground. So they're using two different techniques underground. So they end up with 40-foot rooms.
So when you say that a lot of that's automated, how much work gets done each night that they then come harvest the next day?
So they will do a 20 by 20 room. So, typically the rooms are usually 20 feet wide and 20 feet high. So that saw will come on in and cut I think they're cutting them at almost 2.5 feet across. So, when you're stick your blade in there and you can saw it at 2 to 3 inches per minute, you can cut a lot of stone pretty quickly. And so they'll cut all those horizontal cuts and then they'll come in and make a few vertical cuts. And then it calls home and says, I'm done. And they come in the next morning and do it. Sometimes it breaks down and they have to work on it, but it generally is pretty automated nowadays.
While you were talking, I was looking for my CD of StratGen that I used in grad school that came from Indiana.
Oh,
And
I wrote that program.
yeah, I remembered your name from back when I got it in the early 2000s.
We have a newer one that we call Column now that actually is an automated, kind of approach for making stratigraphic columns. I'm glad it worked for you. So
It did. It did.
yeah, I like to write computer programs that people can use. Mostly because most of the business programs that we have out there don't do what we need to do as geologists. So I ended up having to write things to make those visual things that we use. I got tired of making little blocks on top of little blocks for stratigraphic columns. So I just wrote a program that made the blocks automated for me.
Just a little question on the limestone. How stable is it on the side of a building or in the atmosphere with sun shining on it, rain and that sort of thing?
It's amazing how stable it actually is. The biggest issue that we have with Indiana limestone is usually when it's down near the bottom floors and salt is getting on it, during the salts it's putting out during the winter months. But they often talk about something that they call a case hardening, and I don't know that I actually believe it. The argument is simply that acid rain dissolves a little bit of the stone, and that dissolved material goes, because it is, in many times 13 to 15% porous porosity in it, that stuff goes down in, and then when it evaporates the water away, the calcite comes back and hardens back up the stone again. My life is not long enough to actually do that experiment. So there was an experiment on the top of our building at one time, but then the facility operations didn't know why those stones were up there, so they threw them out. But I would have liked to have been able to continue with that study. But there's no big issues. The biggest issue happens to be with people cleaning the stone. People want to you'll get algae and stuff that'll start growing on it. And the best way to do it is just power wash it, but somebody will decide to use bleach or some other caustic material, and that causes problems with the stone. It makes it bright white, but and 5 years later, you start finding it, starting to deteriorate. we have a study going on right now, and we have a room that's a freezer. It has a cold room on one side and a freezer on the other, and we're doing a freeze thaw study on it right now, where we're using a lot of the different what are considered safe, that you'll see that, oh, it's safe for your sidewalk and safe for your other stuff. And you take it apart and find out it's mostly sodium chloride. So,
Does the change in the ripple sand movement, does that alter the strength of the rock?
yeah, I'm glad you asked that question because I forgot to tell you about that. So I mentioned that there were light and dark laminae, and the light laminae are primarily crinoidal grains, whereas the darker laminae are primarily bryozoan grains. And so because the crinoid grain, so first of all, the crinoids are heavier, so they get transported along and they actually avalanche down the foreset face. So they pinch out both up and down. So I should have shown you that. Whereas the bryozoans, because they get lofted along and they saltate along, they don't really avalanche down. They just sort of float down along the entire foreset. So they extend from the top down to the bottom. And the bryozoans maintain their primary porosity, whereas the crinoid grains, because a crinoid grain is a columnal is essentially a single crystal, they actually cement together more than the bryozoan grain foresets do. So you end up getting this more porous zones and less porous zones. And because the bryozoan grains will loft off and go clear down to the toe set of the foreset, it's often at the bottom of the trough crossbeds where you get all your fluid flow. And so I've been in quarries with petroleum companies. I remember doing one with Marathon a few years ago, and we'd had a big rain, kind of like we just had recently here. And we were looking at a large trough crossbed, and the whole bottom of the trough crossbed was wet. And I argued that primary porosity was actually controlling, and the paleocurrents were controlling the flow of fluid through the stone. Well, they had been arguing this with their engineers for years. And so my field trip was done. They sat around and argued for the next hour and 45 minutes, which I was okay with, but it was something they were trying to understand. So in this sense, the paleocurrent is preserved and fluid flow moves through the stone based on the preserved paleocurrents that are in it.
Another question. Let me see if I can find where I wrote it down. You were talking about how they pump the gas back in the winter and then bring it out. Can you explain a little more about that? I didn't quite understand what.
Yeah, so one of the easiest way to store natural gas is underground. Instead of storing it in a tank. If you want to store it in a tank, you're going to have to liquefy it, and that's a lot of pressure that you need to do. And so it's a lot easier just to shoot it back down a pipe back down into the ground. And so we have that here in our Monroe County and down into Lawrence County. It's called the Leesville Anticline. And so Texas Gas brings gas up from in the summer months and it stores it underground, and then in the winter months pulls it back out again. And they don't seem to lose very much, that they can continue to make a profit.
Okay. Yeah, that was new to me. I was like, I've never heard that. So
What
any other
is the
questions?
porosity that you can store gas in a rock?
Dawn, come back again. I missed the first part of your question.
What is the porosity? What is the void volume within the rock that you have enough volume there to actually store? And
they're going down to the Geneva dolomite, and I'm sorry, but I don't have the numbers on that. It certainly is working out for them, but they're pumping it in the ground a good 700 feet below the ground, and I don't have the numbers on the Geneva.
Okay.
Many of you are familiar that a lot of our world, reservoirs and stuff are all in dolostones. We think about siliciclastic kind of rocks, but generally those dolostones have the most most, secondary porosity in them.
Thank you very much, Todd. I really enjoyed it. I could have listened longer because there was so much to learn and there was so much information, but um yeah, you
Great
need
talk.
to teach a whole class.
Thank you.
Well done. Very well done. Thank you so much.
Appreciate it.
That was
Thank you.
very good, very good.
Yeah,
gonna
thanks
Thank
for all of
you.
you coming here on a Friday evening at 10:18 my time.
Do you have
So-
a minute to talk about Indiana Dunes at all as a place to visit